Okay, hi. My name is Bryn, and welcome back to the voxel file channel. So since I had last left off, I had implemented fixed size voxel worlds. However, this is going to be more of a code-heavy video where I go over implementing automatic synchronization for my GPU library. However, it's probably better if I show. So what you will see that I have here is I have an executor, and an executor is an object which tracks the commands that are being sent to the GPU such that it can optimize those commands and send them to the GPU in an order that will not only be correct, but it will also be efficient. And what you can see is I add tasks to these executors, and I have a lot of tasks, each one for a different series of accesses to the buffers and the images that I'm modifying on the GPU. And you can see all the way down here, if I scroll, when I'm done adding tasks to the executor, I create an executable, and then during the rendering, I call that executable, which calls this function right here. However, we're not going to go over the entire executable function right now. What I want to point out is this line right here between 764 and 769. You see, I have this resources part of the task struct, which takes a closure to a buffer, or alternatively, I can show another example where it will take one to an image. So for example, I am in this task reading from the Mersenne twister buffer, which is basically a buffer which manages random number generation, and then I write that to an image to generate a noise image. But this is actually a really great example. Actually, I'm going to choose this example up at the top. So what you can see here is I have a general staging buffer, and I do a host transfer write. And then in the next task, I do a transfer read and a transfer write to the info buffer. What that's essentially saying is that in the host stage, it's going to do a memory write to the general staging buffer in terms of pipeline barriers. And then in that same pipeline barrier, which will be inserted between write buffer and copy buffer to buffer, it will make the destination it will transfer write on the host, and then it will transfer read on the transfer part of the pipeline. If that doesn't make sense, essentially what is happening is it's saying, hey, GPU, hold up. We don't want to have one of our thousands of processors step over each other's toes. So we have to make sure that all of the processes for this host transfer write is completed before we read from what was written to the buffer. Another example might be, if I scroll down, let me see here. So, for example, I have this is a good example. So, you can see I do the same thing that I just described with the octree staging buffer. I write the octree to the octree staging buffer, and then I copy from the octree staging buffer to the octree buffer. And why you want a staging buffer and a second buffer that is on the GPU is because one lives both on the CPU and the GPU, so it sort of has a highway connection between the CPU and the GPU, such that the CPU can send information to the GPU and vice versa. However, that has some implications, so you don't want every buffer to be host writable, is what it would be called. And so you have the second buffer, which you copy from the staging buffer to the second buffer. But anyways, I digress. You can see that the octree buffer has a transfer write. And then if I scroll all the way down, when I use the octree buffer again, which is here, you can see I do a compute shader read only. So somewhere in between that task, that prior task, and this task, it will insert a pipeline barrier saying, okay, we have written to this buffer, and now we are going to read from this buffer in the next compute shader that takes this buffer. And the GPU command buffer is smart enough to figure out, okay, so it's this write and this compute shader that are conflicting. Okay, we need to synchronize in between those. And essentially how this all works, if it makes it any simpler, is when we take these resources, they're actually closures to these buffers and to these images, but then those are qualified by resolving those resources into the actual resource that they represent. And then we go through these qualifiers, and for each qualifier we keep track of the last access. So this right here, the buffer access or the image access, we keep track of the last access, or we do the default, which is just no access. And then we push back a pipeline barrier for each access, and we just go through the motions adding pipeline barriers. The same with the images, and this is inserted before the task is executed, so before the commands for the task are added to the pipeline. If you want, this is not the smartest way to do it actually. You can actually track the difference between the accesses in order to be more smart about where you will place your pipeline barriers. However, I have not implemented a more efficient way of doing this yet. But the result of what this allows you to do is you can, for example, call a compute shader in a for loop. You can just call that compute shader over and over and over, and it will automatically synchronize between each invocation. Or you can do some complicated conditional function where it will only call a shader under a certain condition, and then it will only insert the synchronization if that condition is met. And so essentially it just reduces a lot of overhead and prevents the coder, the programmer, from having to keep track of this overhead as it pertains to the GPU synchronization. If any of this was interesting, please feel free to keep watching this series. The next video I'm going to release is going to be more visual. However, I really appreciate all of the support I've been given, and I really appreciate your time watching this video. So thank you so much. I hope you have a wonderful rest of your day and a wonderful Thanksgiving. Hope you have a wonderful Thanksgiving if this is coming out after Thanksgiving. But nonetheless, that is all from me. So bye-bye. Thank you so much.